Okay, in the inferencing scenario described here, the population that we're dealing with is the set of all GMU graduates. That's the population, and the properties of the population that we want to know are the average starting salary mu and the standard deviation of starting salaries sigma. Some graduates get less, some graduates get more. So we not only want to know the average starting salary for that population, but also the standard deviation. Now, you have already seen in our inferencing about population means before that in order to make inferences about mu, what we would do is take a sample, perhaps say a sample of 100 or 200 graduates, and I would compute the sample mean x bar. And once I have the sample mean, based on that, I would make an inference about the population mean. And in order to make that inference, anytime I'm making an inference, there is uncertainty. And the basis for quantifying that uncertainty and analyzing that with respect to the inference, the fundamental concept there was the sampling distribution of x bar. So this sample statistic, any measurement that you do on the sample is a sample statistic. And mu is the population parameter. The sample statistic is random, and that's what introduces the uncertainty. Anything that is random has a distribution. So the distribution of the sample statistic, or the sampling distribution, is at the heart of quantifying the uncertainty in the inference. And you remember from the central limit theorem that if the sample size was large enough, then x bar was normally distributed with a mean of mu and a standard deviation of sigma divided by square root of n. So this sampling distribution was at the heart of inferencing about mu. So now we want to make an inference about the population standard deviation, sigma. So what do I have to do? Now in my sample, again, let's say I took a sample of 100 graduating students, I make a measurement of the sample standard deviation. Since I want to make an inference about sigma, the sample measurement that I do is S. And just as with x bar, S is a sample statistic. It is random, it has uncertainty, and therefore it has a distribution. So depending on what sample I pick, I can get slightly different values of S. So the sampling distribution of S would be needed in order to quantify the uncertainty in making inferences about sigma. Unfortunately, unlike x bar, I cannot mathematically express the sampling distribution of S directly. That would make life a lot simpler. Unfortunately, I don't have that. However, what I do have, what I can express mathematically, is the sampling distribution of a related quantity. So here is this quantity that I'm writing, n minus 1 s squared divided by sigma squared. So this looks like a convoluted quantity, but this is the quantity whose distribution I can express, and I will show you that in a couple of minutes. But this is so I don't have a distribution of S. This is what I would really like, but I don't have it. I have the next best thing, that is I have the distribution of a derived quantity. Now if you look at the expression on the right hand side, n is a constant, that's the sample size. Sigma squared, that's the population variance, is unknown, but it's a constant. The only thing random on the right hand side is s squared, okay, it's the sample variance. Hence this quantity chi squared is also random, and therefore it has a distribution. So if I can deal with the distribution of x squared, what you will find later on is that you can reverse engineer the calculations that you wanted to do with S. So I cannot make uncertainty estimates or with the about the inference using S directly. So we will start with chi-squared and then sort of reverse engineer the values that we want. Now, so from now on, in terms of the sampling distribution, we will be talking about the sampling distribution of chi-squared, remembering that it is related to the sample standard deviation and the sample variance through this formula. Okay, so what is the distribution of chi-squared? So here's chi-squared. It's a random variable. Okay, so the first thing to remember is, unlike the normal distribution, remember from the normal distribution, it could range from minus infinity to plus infinity. It looked bell-shaped, and the random variable could range from minus infinity to plus infinity. Chi-squared, since we are dealing with variances here, this is a squared quantity. A squared quantity cannot be negative. So the first difference in terms of the properties of the distribution is it starts from 0, it doesn't exist for negative values, and it goes all the way to plus infinity. So it's one-sided. Okay. The other thing about the chi-squared distribution is that it is not symmetric. Okay, so unlike the normal distribution, which is symmetric around the mean, the chi-squared distribution is right skewed. It has a long tail to the right. It's a tail to the right, let's put it this way. Okay, so it's not symmetric. Okay, there's another aspect of the chi-squared distribution which we need to know, and that's degrees of freedom. Okay, and the degrees of freedom is, in our case, that you'll find is basically sample size minus 1. And what you will find is that the higher the degrees of freedom, the more bell-shaped it looks. So it will never get to be exactly like a bell because it's one-sided here, but the higher the degrees of freedom, the more it looks like a bell. So let's say if you had a sample, rather a degrees of freedom 5, let's say, your curve might look something like this. I'm just drawing it approximately, let's say highly skewed. But if you had degrees of freedom, let's say equal to 50, the curve might look something like this. Okay, so it'll get more and more to look like a bell. So remember, the chi-squared distribution is not symmetric. It starts from 0, okay, and it can go all the way to plus infinity. Other than that, in terms of dealing with calculating probabilities, you deal with it exactly the same way as you did with the normal distribution. In other words, so let's say here's the chi-squared distribution for a certain number of degrees of freedom. You would be asking yourself, what is the area to the right of a certain value? What is the area to the left of a certain value? So again, once again, it's a continuous distribution. You will be thinking in terms of areas to the left or the areas to the right of a value. So the analysis in terms of geometry is exactly the same, but you would, since this is not a convenient shape to calculate by hand, you would have Excel do the area calculations for you, just like you had for the normal distribution. And just like you had norm dist and norm inverse, for the chi-squared distribution, you have chi dist and chi inverse. Those are the two built-in Excel functions to deal with the chi-squared distribution. And in subsequent video tutorials, you will see how to use these built-in functions to make inferences about the population standard deviation. For now, just remember that in order to make inferences about population variance or population standard deviations, you have to make measurements on the sample standard deviation S. Okay, so once you make a measurement of the sample standard deviation, S is your random variable, and the critical thing to remember is we don't know the sampling distribution of S. Rather, we know the sampling distribution of this derived quantity called chi-squared, which is simply n minus 1 S squared divided by sigma squared. So we start our inferencing with distribution of chi-squared, and then we reverse engineer the values that we want from that distribution. And the Excel built-in function is chi dist and chi inverse, And in subsequent tutorials, you will see how exactly to use those functions in order to make inferences about the population standard deviation or the population variance.